Hi everyone. In this particular video, we're going to start talking about conformational analysis. So before we watch this video, make sure that you watched the video on Newman projections, because this is sort of an application of Newman projections. We'll be using Newman projections to understand this concept of conformational analysis. Now, conformations, I have the definition up here. I mean, not like a exact like definition, but like what does it mean? Okay, so conformations are different orientations that are possible in space, different orientations in space, okay, possible due to rotation about sigma bonds. Those are called conformations. What does that mean? Okay, so let's look at an alkane, because again, we're talking about alkanes right now. So let's say this is the molecule of an alkane, and I'm going to define some of these, some of these groups as something, okay? So let's say that what I'm holding on right now here, these are two carbon atoms, okay? So this red and this blue points, these are carbon atoms. Each one of these is a hydrogen atom, okay? So at the end of these lines, which are basically going to, or these connections, these represent bonds. There is a hydrogen atom at the tip here. So if you look about it, if you think about it, what we're looking at here right now is a molecule of ethane, C2H6. There are two carbon atoms, and there are 3 plus 3, 6 hydrogen atoms. This is an alkene. There are only sigma bonds in this molecule, single bonds in this molecule. There are no pi bonds, okay, or there are no double bonds in this molecule. Now, if we focus on the carbon-carbon sigma bond or the single bond, again, let's go to chapter 1, redefine sigma bond. Okay, how do we understand sigma bonds? What is a sigma bond? A sigma bond is formed by the overlap of electron clouds or orbitals along the internuclear axis. That means the electron density in this bond is along the two nuclei, okay, along the internuclear axis. So if this is one nucleus, that's the other nucleus. The internuclear axis is along this sigma bond, okay? That's where the electron density is. How does that help? What does that mean? You know, why is that important? So one of the important characteristics of a sigma bond is that when you have a sigma bond, you could rotate about the sigma bond. Notice how I'm holding one carbon steady and the groups around it steady, and I'm actually rotating the other carbon. Does that break the sigma bond? No, it does not, because that electron density is around this carbon-carbon, or the electron densities along this carbon-carbon bond. We are using that electron density as an axis right now, sort of, to rotate. Okay, so we're just rotating around that axis. So that is one important thing about alkanes or sigma bonds, that you could rotate about this bond. Okay, so now think about it, okay, these are again hydrogens. So starting from here, I can start rotating. And I think at this point, I also want to talk about uh, uh, Newman projections. Okay, so when we were talking about Newman projections, we were looking about a carbon-carbon bond. So this is one carbon, that's the other carbon, blue at the back. So we're looking at the carbon. So notice how that's your front carbon, the back carbon is represented by the circle. Okay, so when you have this, this is one orientation, but now this is one three-dimensional orientation. Things are oriented a certain way. The yellow and the red are like across from each other. They are like the yellow is in front of the red bond, okay? That's how it is. But now I can start rotating, because this is a single bond. I can start rotating about that bond, and groups can start to move. So that means because of this rotation, there are several orientations that are possible in space, or arrangements that are possible in space because of this rotation. So these different orientations are called conformations. So the different orientations or arrangements in space possible due to rotation about sigma bonds. Those are called conformations. So this is one conformation of this molecule, and as I rotate, that's another conformation. Now, I didn't have to rotate that much. I could have rotated by a smaller amount, but that's, again, a new conformation, okay? And as I keep rotating, I get new conformation, new conformation, new conformation, okay? So all of these are basically new conformation. Each one is a conformation in itself. And notice right now I went about 360 degrees, and I could rotate by the tiniest amount possible, and then I will get a new conformation. So there are like a ton of conformations that are possible. Now, ton don't like not literal sense, but there are several conformations possible within this range here. Okay, so those are conformation. What we're going to do here is talk about these different conformations, okay? Are there any conformations that are better than the other, okay? Are some conformations, that is one question that we're going to answer here, are some conformations better than others, okay? And specifically, we're going to define two conformations, okay? And so the first conformation that we're going to talk about is this one here, where one of the carbon atoms, okay, is exactly in front of the other carbon atom. So as we see here, okay, so when we look at this molecule, okay, right now, every bond on this first carbon is in front of bonds on the back carbon. Okay, so they're basically like, what would you call this? This is eclipsing, right? So almost like a lunar eclipse or a solar eclipse or something like that. Okay, this is eclipsing because every bond on the front carbon eclipses a bond on the back carbon. So this is called an eclipsed conformation. Okay, eclipsed conformation. So we have eclipse conformation. And there's another conformation possible where they are like as far apart from each other as possible. Okay, so if we start with this eclipse conformation, and if I start rotating this front carbon, okay, I'm going to start rotating in the clockwise direction. Okay, if I start rotating, okay, the yellow and the red move away from each other a little bit, okay, and they start getting away from each other. Okay, so this is another conformation, but this is not where they are like the farthest apart from each other. Okay, we can do more like that. Okay, and then maybe this. Okay, where the yellow is between the red and the black hydrogen on this back carbon. It is like exactly between the two. Okay. Now, because if I go any further from here, then the yellow is getting away from the red, but it's also getting closer to the black on the back carbon. Okay, so it is like away from one, but it is closer to the other one. We don't want that. So when it is like exactly halfway between the two, okay, and we get to that conformation that it is equidistant from the red and the black here. The yellow is between the two. This conformation is called a staggered conformation. Okay, I will write that term down. So it's called a staggered conformation. Now the conformations are defined, okay, by an angle usually called a dihedral angle. And that is the angle between the red and the yellow. Okay, so the angle here between the red and the yellow. In a staggered conformation, this angle is about 60 degrees approximately. Okay, that's a rough approximation. How do we know that? Okay, let's go back to the angle here. What is the angle here between these two carbon atoms? what parameter would help me determine the angle, the bond angle? We did this in chapter 1. Think about it, hybridization. So the hybridization of this carbon would tell me the bond angle here. This carbon is sp3 hybridized. That means this bond angle must be 109 degrees, the tetrahedral angle. And in the staggered conformation, the yellow hydrogen is in between the red and the black hydrogens, which is 109 bond angle, which means the yellow, the angle between the yellow and the red. Now, we are considering a plane here, essentially, okay? We're trying to consider something here where the yellow is. We're considering there, like, oh, sorry, where the red is, okay? And the angle between the yellow and the red, essentially. That angle is about half of 109 degrees. And so we say it's about 60 degrees. So a staggered conformation is a 60-degree angle between the yellow and the red group, which is a hydrogen on the front carbon and a hydrogen or a bond on the back carbon, okay? So that's the staggered conformation. So staggered conformation. Okay, so those are like two important conformations. So going back to the model again, what would be the bond angle in case of an eclipsed conformation? Okay, so when you're eclipsed, is there a bond angle between any of these groups? Let's say between the red and the yellow or the other blacks? The answer should be no, okay, because they're like right in front of each other. So there's no bond angle. So the dihedral angle is 0 degrees. Now, for the uninitiated, dihedral angle is an angle between two planes. So you might want to like look that up a little bit, okay? Dihedral angle is an angle between two planes. Okay, so an eclipse conformation is characterized by a dihedral angle of 0 degrees, and a staggered conformation is characterized by a dihedral angle of 60 degrees. Now, how do we draw these conformations? So if I have to draw it for ethane, which is C2H6, I'm going to draw the eclipsed conformation like this. Okay, it is C2H6. So CH3, CH3 is what I'm drawing. Okay, that's the front carbon, has 3 hydrogens on it. And then we draw the back carbon, which is going to be a circle. Okay, and the bonds on the front carbon, they eclipse the bonds in the back carbon. Okay, they're like eclipsing the bonds. Okay, so you can barely, so in an eclipse conformation, you should be able to like barely see the groups on the back carbon when it is like properly held actually by me. Okay, something like that. You can barely see the groups on the back carbon. Okay, they're like behind the groups on the front carbon. So the way we show that in our drawings is that's our front carbon, and then on the back carbon we draw bonds right next to these bonds, and then say that they are eclipsed, okay? So they're like exactly behind. That is what we're trying to say to the best possible, by us. So this is an eclipsed conformation, and the dihedral angle here is 0. That means there's no angle at all. A staggered conformation would be where you have hydrogen, hydrogen, and hydrogen, and there is a 60-degree angle between them. So that's when the hydrogen or the groups on the back carbon, they're exactly between the groups on the front carbon. So we have 2 groups on the front carbon, and the group or the bond on the back carbon is between the 2, such that this angle here is 60 degrees. So that is the dihedral angle, okay? So those are the 2 conformations, like the important conformations for for ethane. We're talking about ethane right now. Now, when we go to like other molecules, there are other conformations that would become important. So let's do a conformation analysis right now, okay? And conformation analysis would mean that we're going to do an analysis of how does the energy of the molecule change as the molecule rotates about that carbon-carbon bond. Okay, and to do this conformation analysis, what we're going to do is we're going to plot. Now, again, this is organic chemistry. There's nothing that you have to calculate. We're just going to qualitatively plot something. Okay, so we're going to plot energy versus on the y-axis versus dihedral angle, which is represented by theta, okay? Theta is what we use to represent a dihedral angle. So we're going to plot energy versus dihedral angle. So let's say we start with 0 here, and then you've got 60, 120, and then 180, 240, 300, and 360. Okay, so you're looking at like a complete rotation in space. Okay, so but before we do that, let's talk about the two conformations. So we have two conformations, like the important ones, and then many other in between. But of the two important conformations, one is an eclipsed conformation, okay, which is this, and the other one is a staggered conformation, which is that. Okay, which one of these two would you think is more stable? Should it be the staggered or should it be the eclipsed? Now, with the staggered conformation, notice how the groups are oriented away from each other, okay? And because of that, what happens is the staggered conformation is more stable compared to an eclipse, okay? So staggered conformation is more stable. Now, you could rationalize it in different ways, okay? One way of saying this could be that, okay, when you're in the eclipsed conformation, okay, and again, this is more of like a classical approach of explaining this, but I'll also talk about like a more contemporary or like a newer version of how we understand this, okay? So one way of understanding this could be that, okay, this here is a bond, and a bond is basically electron. So there's some electron density here. This line here is also a bond, which means electron density. So there's electron density here, there's electron density here, and it is very easy to see how the electron density here would repel the electron density at the back. Okay, so there's going to be some repulsion. So they're not going to be happy. Like in fact, all of these bonds, okay, there is electron density that's repelling each other. So they will not be happy being next to each other. So what would they like to do? They would like to push away from each other. So this bond, as it rotates, it's actually pushing away the electron density away from each other. And when you get to the staggered conformation, okay, when these groups are like the farthest away from each other, notice how the electron density here is away from the electron density here, but it's also away from that electron density, or on this side, right? This electron density is away from this electron density as well as from that electron density. So all that electron density is as far apart as possible. So that could be a very crude way of explaining why a staggered conformation is more stable than an eclipsed conformation. Now, a newer way of understanding this relates to molecular orbital theory, okay, which is a little bit, I mean, I think unless you've done this and you know, it's a little hard to understand, but if we consider a particular sigma bond, okay, let's say this sigma bond, then the sigma star orbital for that bond should be here, like across from this bond itself in the opposite direction. There is something called a sigma star orbital, the anti-bonding orbital. And the sigma bond for this orbital is here along this bond because that's the sigma bond, okay? And the sigma star for that would be across from it. So when you're in this staggered conformation, what you can see is that the sigma bond here, which is electron density, full of electrons, it lines up with the sigma star of this other bond, which is across from it and pointing away from it. Okay, the sigma star here and the sigma bond, they would align with each other, so there will be some overlap. So that overlap stabilizes the molecule, and it would be the same on the opposite end because there would be sigma star coming down here and there's sigma electrons here, and they would basically interact, and that stabilizes. And it's true for every bond actually. So that interaction stabilizes the staggered conformation, okay? So, but I think what we're going to say here is, just to summarize it, we're going to say staggered is more stable than eclipsed, okay? Staggered conformation is more stable than eclipsed. Okay, now let's do a conformation analysis. And again, if you look at the book actually goes over the numbers. I'm not going to quantify this interaction anyway, okay? But let's say at 0 degrees dihedral angle, okay? A dihedral angle of 0 degree would mean that it is an eclipsed conformation. So this is where we are, okay? So the molecule is eclipsed. The ethane molecule here is in an eclipsed conformation, okay? So it's an eclipsed conformation. That's the dihedral angle. Now, since this is an eclipsed conformation, that means the energy for this conformation, when the dihedral angle is 0 degree, it should be high. And as you move away from the eclipsed conformation, now whichever model you use to understand the stability, okay, what you're doing is you are either moving these electron densities away from each other, or if you think about the stabilization because of the orbit or the overlap. Now, in an eclipse conformation, notice how the sigma star for this bond would be here. The sigma star for that bond would be here. They're both empty, so there's no constructive or no useful interaction there. Okay, so that does not stabilize. Okay, but when you're this eclipse conformation, and as you move away, you are getting to a staggered conformation, which would result in then the interaction, or the electron densities are farther away from each other, whichever way you understand this. Okay, so when you start with the eclipse, it is the least stable in some sense. Okay, it is the least stable. So in fact, I think I'm going to say it is more stable. Okay, in fact, staggered is the most stable of all possible conformation, and eclipsed is the least stable of all possible conformations. Okay, so we start with the eclipsed, and as we move away from it, we are relieving some of that repulsion, or we are trying to build in that overlap between the sigma and the sigma star. So the molecule starts feeling better and better. It is feeling more stable, and we get to the staggered conformation, which is now a 60-degree bond dihedral angle, and this is very stable, okay, compared to, relative to the eclipse where we started. So let's just say that, you know, this is the energy of the eclipse conformation, okay? And when it comes to a staggered conformation, that is the energy of the staggered conformation. So we start with the eclipse, and as we move away from the eclipse, okay, as the dihedral angle increases from 0 to like 60, as the dihedral angle increases from 0 to 60, the energy drops, and it is the lowest at 60 degrees. When you hit that 60 degree, it is the lowest possible because that is the most stable conformation. So when something is stable, the energy is the lowest, or most stable, then the energy should be the lowest. Okay, so we are at the staggered conformation. Now, as you move away from the staggered conformation, okay, as you move away from a staggered conformation when you move away from staggered conformation, notice how you're trying to build in another eclipsed. And so now if we track the red and the yellow bonds, they have a dihedral angle of 120 between them. And at this point, there is an eclipse conformation. So at 120 degree dihedral angle, okay, in fact, I'm going to draw this in, okay, at a 120 dihedral angle, the energy of this system is the maximum possible because you're at another eclipse conformation. Now, I know my graph is probably not the best, like textbook, okay, but that's what you get. So you're at 120, you're at again, an eclipse conformation. And then as you rotate, you are go to 180. Now the red and the yellow are like across from each other. That means the dihedral angle must be 180 degree between them. And this is a staggered conformation, okay? So that means you're stable again. So you go down again to 180, and then again it goes up, goes down, and then goes up. So it basically goes up and down. So that would be the, sorry, why did it go down all the way to there? Didn't have to. So the energy goes down, 180 goes up, and then goes up again, okay, if that is the thing. So we've got a conformation analysis of ethane now. So conformation analysis is basically the change in energy as a function of conformations or as a function of dihedral angle. So it is the max when it's an eclipse conformation, goes down to a staggered, climbs up again to another eclipse, goes down, and then keeps going up. So you basically go up and down, okay? And there is no other change here. Okay, so now that we've done propane, let's think about adding something to this molecule. So let's say we have, we've done ethane now. So let's move on to propane, okay? Propane is C3H8, okay, so it has an extra carbon, okay, C3H8, okay, it's an extra carbon. So now we have CH3, CH2, and then CH3. So there are two carbon-carbon bonds here. Now we cannot do a conformation analysis. In fact, I don't want to say that, okay? But for now, I think what we'll do is we will focus on one carbon-carbon bond at a time. We will not look at several bonds. In fact, it becomes too complicated, okay? So let's say we are doing the conformation analysis about one of these carbon-carbon bonds, okay? So this is propane. Now I just modified that ethane molecule to bring in a propane. Again, carbon, carbon, and then carbon. These are three carbons, and all the other groups are hydrogen. So C3H8, okay? So these bond angles are all like 109 degrees. That's what it is here, okay? And we can only do conformations about one carbon-carbon bond. So let's focus on that carbon-carbon bond, the black carbon-carbon bond here again. Okay, and so if we look at the black carbon-carbon bond, okay, one of the carbons is a methyl, it's a carbon with 3 hydrogens. The other carbon has 2 hydrogens and then a methyl group connected to it. And that is what we're seeing here. One carbon has 1, 2, 3 hydrogens, and then the other carbon has 2 hydrogens and then a CH3 group connected to it. Okay, so if we did a conformation analysis on propane now, so let's think about it. Okay, that is one conformation of propane, okay, and we're looking at one of these carbon-carbon bonds. Now let me draw this in 3 dimensions so that you know what exactly we're looking at here. So I'm going to say that we're looking at an eclipse conformation of propane, or at least that's where we are starting. Okay, we're looking at an eclipsed conformation of propane. There we have that. Okay, so if I look at this carbon here, I will see a hydrogen at the top, on the back carbon here, there's a methyl group behind it. And then there's a hydrogen on the wedge, hydrogen on the wedge, hydrogen on the dash, hydrogen on the dash. And that's exactly what I'm showing here. This is what you're seeing. So I have hydrogen top, methyl on the top, hydrogen on the wedge, hydrogen on the wedge, hydrogen on the dash, hydrogen on the dash. Okay, so that is the conformation here that we're looking at. And this is an eclipsed conformation. Now again, as you can imagine, this eclipse conformation should not be that stable, okay? And in fact, if we were to do a conformation analysis, okay, again, energy and dihedral angle, okay, this eclipsed conformation should be the least stable, and it will have some energy here, okay, at 0 degrees. Now, let me ask, is this energy, the energy of this eclipse conformation, should this be higher or lower than propane? Okay, sorry, ethane, the first molecule that we looked at. So ethane did not have the CH3 group, okay, that is ethane. So should it be higher or lower? And if you think about the simple model where we talked about electron density, right? What you notice is here, you have electron density here, but there's additional electron density here. So there's going to be more repulsion here. It's an electronic repulsion, okay? The two electron densities repelling each other. So this should not be, this should be like more unstable compared to ethane, the eclipse conformation. Now, as we rotate, okay, now we're following the red bond and this yellow carbon-hydrogen bond, okay? The red carbon-carbon bond as a reference for this carbon-hydrogen bond in yellow. Okay, as we rotate, we start with the eclipse conformation, and if we rotate, we go to a staggered conformation. Okay, this should be stable, okay, compared to the eclipse. And as we rotate more, we go to another eclipsed. Okay, now notice how earlier the yellow carbon-hydrogen bond was eclipsed with the red carbon-carbon bond. But now there's another carbon-hydrogen bond that's eclipsed with the carbon-carbon bond. So these conformations are exactly the same, the first eclipse and this eclipse. And as we rotate further, we go to a staggered, okay, where everything is like the farthest away possible. And we rotate further, we go to another eclipse, which should be the same as every other eclipse, and the same is true for the staggards. The staggards are also going to be the same as other staggards. And as we rotate further, we go to the next staggered and then to the next eclipse. But the energy of these eclipse conformations, they should be higher than the energy of the staggered conformations. Okay, so that means when we drew a conformation analysis for propane, we're going to get something similar. It will go down to the staggered, go up, come down, go up, come down, things like that. That is how it would follow. But this energy max must be a higher number than the energy max for ethane because you have more repulsion now. Okay, so that's the conformation analysis. So please look at the textbook. Try to draw out some of these conformations and then, look for the sort of interactions that you would have. And so what we're going to do is in the next video, we're going to talk about conformations for butane, which is a little bit more complicated, but we will fall back on this information and try to build from there. Okay, I hope that was helpful. Bye.